Hi everyone. In this video, we'll be discussing comparison tests for determining whether series converge or diverge. In particular, we will derive a comparison test for series convergence. We'll understand the uses and limitations of that comparison test, and then we will learn a limit comparison test to apply in cases where the comparison test fails or is difficult to apply. So to begin with, before we officially write down the comparison test, I want to think through an analogy. So imagine that you have two different series, and I'm going to represent each of these series with a balloon. And imagine that you know one of the series, the sum of the ANs, is always less than one of the other series, sum of the BNs. So this is represented sort of by the two balloons, the dark orange balloon and the light orange balloon. Now imagine these balloons are made up, they're identical, they have identical properties. One just happens to be slightly less full than the other. And now imagine those balloons get inflated. So as they inflate, you might wonder, when are these balloons going to pop? Well, if you know that the bigger balloon doesn't pop, then the smaller balloon also can't pop, right? They're identical. So if the larger one doesn't pop, then the smaller one doesn't pop. But similarly, if we were to blow this up and we knew that the smaller one popped, then that would tell us that the bigger one must also have popped because, well, it was bigger than the smaller one and they're identical balloons. Okay. Now notice that in this analogy, if I knew that the larger one popped, that doesn't tell me anything about the smaller one. It may or may not have popped. But in certain cases, right? So in the case where the smaller one pops, I know the larger one must pop. Or if I know that the larger one doesn't pop, then I know the smaller one didn't pop as well. Now, how does this relate to series? Well, imagine I have these two series, and suppose I know that the terms of the series are ordered. So I know that the nth term of the series, sum of the ANs, is less than the nth term of the sum of the series BN for all n beyond some certain value. So sort of eventually all the terms of one sequence are bigger than the terms of the other sequence. Well, then if I know that, if the larger series converges, the smaller series must also converge. In the balloon analogy, that's like saying that the larger balloon didn't pop, so the smaller balloon doesn't pop. On the other hand, if I know that the smaller series, sum of the ANs, diverges, then the larger series, sum of the BNs, must also diverge. In that balloon analogy, that's like saying that the small balloon popped. That tells you that the larger balloon must also have popped. Okay, let's see in practice how this comparison test can be useful in studying series. So imagine you're given this series and asked to determine whether it converges or diverges. Now, when you first look at this series, it looks almost like a p-series, right? It looks very similar to sum 1 over n cubed, which we know that this series converges by the p-test. Right? So recall that the p-test tells us if I have a series of the form 1 over n to the p, if that p is greater than 1, the series converges. If that p is less than or equal to 1, it diverges. But this is a different series, and so I'd like to use what I know about this series to help me here. Okay, well, the first thing I want to note is that 1 over n cubed plus 1, when compared to 1 over n cubed, well, this has a larger denominator, which means that this entire expression is smaller. So 1 over n cubed plus 1 is less than or equal to 1 over n cubed. And so we know here that the sum of these terms, this series converges. So the larger series converges, which tells us that the smaller series must also converge. So since 1 over n cubed plus 1 is less than or equal to 1 over n cubed, by the comparison test, the sum of 1 over n cubed plus 1 converges since the sum of 1 over n cubed converges. So again, let me point out a couple of things here. The first is that when we're comparing a series, we're always comparing it to something else. And that something else, we have to be able to determine whether that something else converges or diverges. So in this case, I'm going to compare it to this, and I know that this thing converges. Now, because I know this converges, and because I know that the series I'm interested in, its terms are smaller than the series that I know converges, then by the comparison test, the smaller series must converge since the larger series converges. Okay, let's take a look at another example. Suppose you're asked whether the series 6n squared plus 1 over 2n cubed minus 1 converges or diverges. Now, in this case, it's maybe not quite as obvious what series we may want to compare this to. So I'll begin first by just looking at the terms of this series. So I have 6n squared plus 1 over 2n cubed minus 1. And I could start thinking about different ways that I could modify this expression. In particular, I could maybe try and get rid of these sort of plus 1 and minus 1 terms sitting in the numerator and denominator respectively. Let's think about those each in turn. If I were to drop the plus 1, I would be making the numerator smaller, which would make the overall expression smaller. So if I drop that plus 1 in the numerator, I'm going to make this expression smaller. Okay. Likewise, if I were to drop this minus 1 in the denominator, that would make the denominator larger, but making the denominator larger makes the entire expression smaller. But now I have something that I can simplify, right? So I have a common factor of 3 in the a common factor of 2 in the numerator and denominator. So that can just become a 3 in the numerator. And I have a factor of n squared in the numerator and a factor of n squared in the denominator. I'll be left with an n there. And so I end up with this. Okay. Now, let me ask myself, what do I know about the series 3 over n squared, or sorry, 3 over n? Well, I have a constant 3, which I can factor out of the sum. And this is a p-series, sum 1 over n. This is a p-series with p is equal to 1. And so it diverges by the p-test. Now, what do I know here? I now know that the smaller series diverges. That tells me that this larger series must also diverge. So since 6n squared plus 1 over 2n cubed minus 1 is greater than or equal to 3 over n, and the sum 3 over n diverges, then the sum 6n squared plus 1 over 2n cubed minus 1 also diverges by the comparison test. So smaller series diverges, the larger series must also diverge. So again, we compare the series we're interested in to a different series, which we can apply a different test to determine convergence or divergence, in this case, divergence. We have that the smaller of the two series diverges, therefore the larger series must also diverge. Now, occasionally these comparisons can be not entirely straightforward. So here's an example of another series. So if I'm going to try a comparison test, I'm first going to actually a different color. First going to just look at the terms of my expression. Now, again, where this can get tricky is I'm not really immediately sure whether I should try to make this bigger or smaller. But I might start by noticing I have this -2 here. Maybe I could get rid of that. If I were to get rid of that, that would actually be making, sorry. If I were to get rid of this -2, I'd be making the denominator larger. Making the denominator larger makes the entire expression smaller. So now here, maybe it's not immediately clear what I could do with this natural log. I need to make it smaller, right? I want to sort of keep moving in that same direction. So I could sort of, ask, well, I don't know, what's something smaller than this? But maybe I don't immediately know something, right? So already we sort of see one of the difficulties that can occur with these comparison tests is sort of you don't always know what the appropriate inequality to use is, okay? Now let me actually offer a different route to reach a solution here, which requires a little more creativity. And this comes from the notion that I actually have some intuition that I think this will converge. And the reason I think this will converge is I know that natural log of something is always less than or equal to that thing. So in general, natural log of x is less than x. Okay. So here, this is like my x, sorry, less than or equal to x. So I can just apply that. And now if I look at this, I mean, I have some constants, but I start roughly thinking that this is like n over n to the fourth. That's 1 over n cubed. And that series converges. So now I get it in my mind that I want to prove that this converges. And if I want to show that this thing converges, if I think this converges, then I need to find a larger series that also converges. Okay. So that now limits what I can do, because now if I'm going to make this larger, I either need to make the numerator larger or the denominator smaller. Okay. So what could I do down here to make sure that I'm subtracting off more? Well, I could actually replace this 2. I could subtract off even more than 2. I could subtract 2 times n to the fourth. Now notice that again, because n is, I'm imagining is like 1, 2, 3, 4, 5, so on, right? So essentially n to the fourth is always bigger than 1, so subtracting 2 times n to the fourth is always subtracting at least as much as 2. And so this becomes 1/10 n over, now this denominator just simplifies to, I've got 3 to the fourth minus 2 to the fourth. That's just n to the fourth. And this becomes 1 over 10 n cubed. Now, what do I know about the series 1 over 10 n cubed? Well, I can factor out a 1/10. And now this converges by the p-test, because I have p is equal to 3, which is greater than 1. Okay. And now I have the larger series, which converges. Oops. And since the larger series converges, since ln of 1/10 n over 3 n to the fourth minus 2 is less than or equal to 1 over 10 n cubed, and the sum 1 over 10 n cubed converges by the p-test, then by the comparison test, the sum natural log of 1/10 n over 3 n to the fourth minus 2 also converges. So in this example, we see that you can use the comparison test sometimes, but it may not always be easy, right? So here I had to use sort of an inequality that, again, you may or may not have known off the top of your head. Even then, I sort of had to be a little careful here to come up with some special inequality in the denominator that would also work out in my favor, and then it would work. So the comparison test is great when it works, but it's also always, it can be hard to figure out, like, will this actually not work? Or am I just having a difficult time proving sort of the right inequality? It's not always straightforward to apply, as I hope this example has shown. Let's look at one more example. And as you first look at this example, you may say, oh, we already did this. But we actually looked at the case before where you had a plus here and a minus here. So I've just swapped those signs. Well, before, right, so we essentially took this expression and we just got rid of the constant pieces. So if we were to get rid of the constant pieces here, right, I'd say, okay, I'm going to get rid of this -1. That's going to make the numerator bigger. So I'm making this bigger. In the denominator, I'm going to get rid of this +1. That's going to make the denominator smaller, which also makes this bigger. And sorry, this gives me 3 over n, right? And we observed last time, right, that the sum 3 over n diverges. This is, again, a p-test. Okay. But note that now that's no longer helpful. In the previous case, because our plus and minuses were switched, our inequality here was switched. And so in that case, we knew that the smaller thing diverged. But now what we know is that the larger thing diverges. And that doesn't tell us anything about the smaller thing, right? Just because the big balloon pops, you don't know whether the smaller balloon has popped or not, right? So in this case, we would say if you're comparing this series to this series, the comparison test is inconclusive. Okay. But we can work a little bit harder. Okay, because in your gut, you might be thinking, well, that plus and -1 sort of shouldn't be making that much of a difference as to whether this converges or diverges. Okay, so maybe what I'll do instead, right, in my gut, I still sort of think I've got an n squared over an n cubed. That should be like a 1 over n. It should diverge. Okay, And so I could be a little more sophisticated here. If I think it diverges, I need to find something smaller, which also diverges. So that means I need to make the numerator smaller. Well, instead of just subtracting 1, what if I subtracted n squared, right? N squared will always be greater than or equal to 1. When n is equal to 1, they're equal. And then n squared will be larger, so you'll be subtracting off more. Let's make the whole thing smaller. And the denominator, let's see, I could make that bigger. That would make the whole thing smaller. So instead of adding 1, I'll add an n cubed. Well, that would give me 5n squared over 3n cubed, which would give me 5 over 3n. And now the sum 5 over 3n, that's really the same as 5/3 times the sum 1 over n, which again diverges. Okay. And so we can still conclude that this series, since 6n squared minus 1 over 2n cubed plus 1 is greater than or equal to 5 over 3n, and the sum of the smaller thing diverges by the p-test, then the series 6n squared minus 1 over 2n cubed plus 1 diverges by the comparison test. Sometimes we just would say by comparison. So again, very small changes in the problem can necessitate totally different methods for setting up an appropriate inequality. Now, that doesn't mean that comparison test is going to work in every possible case. But as I hope you've seen, even when it does work, it can be sort of difficult to apply because you need to establish these certain inequalities. Okay. So the comparison test is great, but only when you can find an appropriate series to compare it to. And when I say an appropriate series to compare it to, there are really two pieces of that. The first is that you have to be able to establish some inequality between the two series. And the second is that you have to be able to determine whether or not that series converges or diverges using some other test you know. So while sort of in theory, it's a really nice test to use, in practice, it can be difficult to apply, even when it actually may work. So let's pause for a moment then for a knowledge check. I want you to use the comparison test to see if you can determine whether the series below converges or diverges. The video will pause. You'll be given a moment to try this problem using the comparison test, and then we'll come back and look at it together. Okay, great. Let's take a look at this series. So the first thing I want to think about is, well, what can I say about this sine of n squared over n squared plus n? Well, I really don't like that sine of n. But what I do know is that sine of anything is always between -1 and 1. And so if I square it, the numerator will always be less than or equal to 1. So I know that this is less than or equal to 1 over n squared plus n. Okay. Now I've made this larger, so I need to continue in the same direction. Okay. So if I'm going to make this larger, I need to make the bottom smaller. Okay. Well, I could make the bottom smaller by getting rid of that plus n. Well, now what can I say about this series? This converges. Again, it's a p-series with p equal to 2, which is greater than 1. And so I can conclude that since sine of n squared over n squared plus n is less than or equal to is less than or equal to 1 over n squared. And since 1 over n squared converges, then the sum sine of n squared over n squared plus n also converges by comparison. So again, here we had to make use of sort of an inequality, right? That sine of n is always between -1 and 1. Therefore, sine of n squared is always between 0 and 1. Making use of that, and then making the denominator smaller by dropping a term out gives us this. This is a series we can determine the convergence of or divergence for. In this case, it converges. And now, because you have the larger series converging, the smaller series must also converge. Again, the comparison test is great, but it can often be a little tricky to establish the inequalities we've been talking about. And so sometimes we'd like to just sort of be able to look at a series and say, well, I think this behaves like 1 over n cubed or 1 over n squared. And so we'd like to be able to take advantage of sort of the idea that one series should roughly behave like another, and be able to apply a type of comparison test without having to worry about the inequality. That's where something called the limit comparison test comes in. So suppose you have two series and suppose they both have positive terms. So an is greater than 0 and bn is greater than 0. Again, that was also a condition for the comparison test. You needed series with positive terms. But now notice that I don't require that either of them be larger than the other, right? So I'm in the comparison test, I needed to know that like an was less than or equal to bn for all n, at least beyond some cutoff. Here, I'm making no such assumption, just that an and bn are positive terms. If, when I compute the limit of this ratio, so when I look at the limit as n goes to infinity of an over bn, if I take that value and say it's equal to c, where c is greater than 0 and c is finite, then the series an and bn either both converge or both diverge. The limit comparison test doesn't tell you anything if that limit is equal to 0 or is infinite, okay? So in this case, we're only able to conclude something if c is a non-zero real number, okay? But if c is a non-zero real number, then the limit comparison test tells us that these series either both converge or both diverge. Let's see how to use this in practice. So again, let's go back to this series before. We were able to determine that this series diverges, but I want to show you sort of some of the advantage of this limit comparison test. So again, when I looked at this, right, my sort of thought was, well, if I just look at the highest powers in the numerator and denominator, that's like a 6n squared over 2n cubed. And as n gets really large, that -1 or +1 isn't going to make a lot of difference to the actual value. So this should behave roughly like 1 over n. So I think, and you could say, well, there should be a 3 there, but again, the 3 is not going to make much of a difference. I really think this should behave like n squared over n cubed or 1 over n, okay? So for the purposes of the limit comparison test, this is going to be like my an, and this is going to be my bn, okay? So I want to look at then the limit as n goes to infinity of an divided by bn. So if I write out what that is, that's the limit as n goes to infinity of 6n squared minus 1 over 2n cubed plus 1 all over 1 over n. Now, I have a fraction divided by a fraction. That's the same as top fraction times the reciprocal of the bottom. But multiplying by the reciprocal of the bottom is just going to multiply the numerator by n. So this will give me 6n cubed minus n over 2n cubed plus 1. Okay. Now I can look at this. I see the highest power in the numerator and denominator are both n cubes. The limit as n goes to infinity. I'm going to divide every term by n cubed. So this will be 6 minus 1 over n squared over 2 plus 1 over n cubed. And notice that as n goes to infinity, this term goes to 0, this term goes to 0. And so this limit is 3. So notice that this value, right, is greater than 0, and it's finite. It's greater than 0 and finite. Okay. And so the limit comparison test tells me that this series and this series either both converge or both diverge. Well, I know this series diverges. This diverges by the p-test. Okay. And so now I know this diverges by the p-test. The limit comparison test tells me these either both converge or both diverge. Well, they both have to diverge because I know this one diverges. Okay. So the series 6n squared minus 1 over 2n cubed plus 1 diverges by limit comparison to 1 over n. Okay. So the nice thing here is that I don't have to establish any inequality. The downside maybe is that I've got to calculate this limit, right? Okay, so you know, it's not all it's not always like easy, right? You're trading off an inequality for a limit. But in some cases, this can be a little more straightforward to deal with than trying to find, to establish some appropriate inequality. And in particular, it just allows me to sort of say, I think this should act like 1 over n. And essentially calculating this here, what I'm saying is, you know, in the limit, this is really like 3 times this. Right? And when we did that direct comparison, right, we actually had a 3 there, right? So what this is really saying is as n gets large, this series really behaves like 3 times this series. But this series diverges, so this must also diverge. Now, of course, you could pick the wrong thing, right? So, for example, you could say, well, what if, I don't know, what if I maybe messed up here and I said, you know, I think because there's an n cubed in the denominator, maybe I should compare this to 1 over n cubed, right? What would happen if I did that? Well, if you did that, let's see what would happen. Okay. So if you tried to do limit comparison to 1 over n cubed, then you'd have your an would be the same, your bn would now be 1 over n cubed. And now this limit as n goes to infinity, do top times reciprocal of the bottom, you'd get 6n to the 5th minus n cubed over 2n cubed plus 1. And this limit, the largest power is n to the 5th. If you divide by n to the 5th, you'd get limit as n goes to infinity of 6 minus 1 over n squared over 2 over n squared minus 1 over n to the 5th. The top is going to 6, but now the bottom would be going to 0 because each of these terms would be going to 0. So you have something going to 6 over something going to 0. This limit would be infinite. And because you have an infinite limit here now, you cannot conclude anything from the limit comparison test. So often if you sort of choose the wrong thing for limit comparison, right, you're going to end up getting either infinity or 0, depending. but you're going to get something that tells you all of a sudden that the limit comparison test no longer applies. All right, let's look at another example now. Okay, so again here, imagine you're given the series 3 over square root of n cubed minus n squared plus 5. Okay. Now again here, this is where I think I really want to think about as n gets large, well, nothing is changing in the numerator, but as n gets large, sort of the largest power of n ought to win out. Like it's going to, n cubed is going to be way bigger than n squared as n gets really, really large, and certainly going to be really much bigger than 5. So when I start thinking about what should I try limit comparison to, I often think about, well, what if I just dropped out the lower powers of n? So in the numerator, I don't have any powers of n, so I'm going to leave that alone. But in the denominator, what if this was just this? Now, if I simplify this a little bit, I can sort of think about the 3, if I want to pull that out, and then I would get 1 over, now, oops, I could think of this as being n cubed to the 1/2 power. And so this would be n to the 3/2. So when I want to do limit comparison, I'm actually going to forget about that constant 3. I'm going to try limit comparison to 1 over n to the 3/2. Now I know that this series converges by the p-test. I have 3/2, which is bigger than 1. Okay. So if I can do limit comparison, and I get a limit that's bigger than 0, but not infinite, then I'll know that this series also converges. So let's see what happens here. So I want to do the limit as n goes to infinity of an over bn. Now, one of the things you'll start to figure out is that often just simplifying this expression an over bn is a lot of the work. And if you don't want to carry that limit along, you can just sort of go off to the side and calculate this. So this would be like 3 over square root of n cubed minus n squared plus 5 over 1 over n cubed, or sorry, n to the 3/2. Okay. Now, let's see, that ends up being what? That ends up being 3 times n to the 3/2 over the square root of n cubed minus n squared plus 5. Okay. Now, this is where it might actually be helpful here to convert back. This is the square root of n cubed. Because now I can write this as 3 times the square root of n cubed over n cubed minus n squared plus 5. Now, the reason that's helpful is that when I come here now to calculate the limit, be careful there so that I don't want that to look like a cubed root. 3 times the square root of n cubed over n cubed minus n squared plus 5. Well, we can certainly pull the 3 outside the limit. We can always pull a constant outside the limit. But we can also move the limit inside this square root function, because the square root function is a nice continuous function. So this is 3 times the square root of this limit. Now, this is where you could divide everything by n cubed. We're gonna be doing lots of these limits, so we're gonna want to get fairly quick at them. I have the same highest power in the numerator and denominator, so it's just the ratio of their coefficients. This limit is just 1. So this is 3 times the square root of 1, or again here, just 3. Now, again, this is greater than 0, and it's finite. So the limit comparison test tells me that these two series either both converge or both diverge. but I know this series converges because of the p-test. And so this series converges by limit comparison. To 1 over n to the 3/2. So again, it's a nice test. I didn't have to worry about trying to set up any sort of tricky inequalities here. I could just sort of write out, what I thought it should behave like, use the limit comparison to show that in fact it does behave like that. And so since this converges, this also converges. All right. And let's look at one last example here. This is the sum 2 over square root of n minus natural log of n. Okay. Now, again, this is where I sort of have to think about, what are highest powers here, because I have a natural log of n. Now, you'll remember earlier, right, we used this fact that natural log of n is less than or equal to x. And in fact, natural log actually grows slower than sort of x to any power here, right? So in particular, we sort of discount this when comparing it to powers of n. So if I think of this as n to the 1/2, this is natural log of n. This is the higher power, okay? So, oh, sorry. That should be ln of n less than or equal to n to the p, okay? For any positive power. Okay. So when I'm looking at this, I really start thinking, this ought to behave like, well, in the top, I just have a constant. In the bottom, my highest power is like n to the 1/2. And I know that this diverges by the p-test. So now what can I do? Well, I can try limit comparison to this. So I look at the limit as n goes to infinity of 2 over square root n minus natural log of n over 1 over n to the 1/2, or for these purposes, probably square root of n makes more sense. Okay. This is the limit as n goes to infinity. Doing a bit of algebra, this is 2 square root n over square root n minus natural log of n. Okay, now, this is where evaluating this limit might be a little tricky, okay, but let me divide every term, the numerator and the denominator, by the square root of n. So it'll be the limit as n goes to infinity of 2 over 1 minus natural log of n over square root of n. Okay. Now, of course, you have the question now of sort of what's this limit? So you may even here have to go off to the side and say, what's the limit as n goes to infinity of natural log of n over square root n? Well, as n goes to infinity, this goes to infinity, and this goes to infinity. I have an indeterminate form. I could use L'Hopital's rule here. So if the limit as n goes to infinity of the derivative of this over the derivative of this, so let's see, that's n to the 1/2. So that ought to be 1/2 n to the minus 1/2. Well, let's see, what does this come out to be? The limit as n goes to infinity. This is 1 over n. This is really 1 over 2 square root of n. And so simplifying this, I get that this is the same as 2 over square root n, and that limit is 0. So now I know, because this limit exists by L'Hopital's rule, this limit is equal to this, so this limit is also 0. Now, that tells me that the limit of this term as n goes to infinity is 0. So this limit is 2 over 1 minus 0, or 2, which of course is greater than 0 and finite. And so the limit comparison test holds here. And because this series diverges, this series must behave the same by the limit comparison test. So it also diverges. So we've seen here several examples. Again, the benefit of the limit comparison test is I get to just sort of look at it and think, oh, I think it should behave like this. And then limit comparison allows me to say that, yes, in fact, it does behave in the same way as that series does. Of course, it's not without its challenges. As we've seen here, you can get some tricky limits to take. Just as with the comparison test, you can get some tricky inequalities that you need to establish. So none of these are perfect or foolproof or even necessarily easy, but they are all additional tools that we can add to our sort of toolbox for dealing with convergence of series. So now that we've looked at several examples using the limit comparison test, let's pause for a quick knowledge check. So I want you to use the limit comparison test to determine whether the series below converges or diverges. So I have the sum n squared plus 3n minus 1 over 4, or over n to the fourth minus n plus 1. So the video is going to pause, take a second, and see if you can determine whether this series converges or diverges using the limit comparison test. All right, so quickly, we'll go through this. Again, you first need to determine what you want to do limit comparison to. And if I look at this series, I think, well, my highest power here is an n squared, highest power here is an n to the fourth. So this ought to behave like n squared over n to the fourth, or 1 over n squared. Okay, I know that this converges, right? Because this is a p series, and p is greater than 1. All right, so then I need to calculate the limit as n goes to infinity of an over bn. Okay. Now, again, we've done many limits of this type, so I'm not going to write out the full details here. In this case, when you calculate this, you should actually get here that this limit is 1. Okay. But this limit is, again, greater than 0 and finite. And so since this converges, the limit comparison test tells us that this series must also converge. So we'll wrap up today's discussion with just sort of a few remarks. The limit comparison test is really nice in situations where you feel like you understand how a series should behave, but maybe you can't exactly prove the inequalities you need to use the comparison test. In terms of both of the comparison tests, both of them require that the terms in the series, or at least all the terms beyond some cutoff, be positive. So we still have a big open question, which is how we deal with a series like, say, minus 1 to the n over n. That series is what we'll shortly call an alternating series, right? So when n is 1, you get minus 1 over 1. When n is 2, you get 1 over 2. So and then the signs alternate. So there's never some point where the series becomes always positive, right? It's always alternating sign back and forth. And so far, none of the tests we have available to us really deal with those, except really, I guess, maybe the test for divergence. But again, that would never allow you to conclude that something converges. So what we're going to see moving forward is that we need additional tests that will help us deal with series that don't always just have positive terms. And so that's where we'll be going moving forward. But before we get there, you have a chance on the homework and quiz to practice using comparison and limit comparison tests. And as always, reach out if you have any questions or need any help.